starting with information that I collect. First of all, we need to start with having some soil sample information. And for the most part, the growers that we work with actually pay us to take the samples. They would rather have us just pay us to do it for them. And as a part of that process, there's sort of information that we have to coordinate with the growers before we can go out and sample, obviously. So we get field location information from them. And they're also involved with sort of the decision-making around which lab we send the samples to, and also what analysis package is run with the labs, because they're paying for all of that too. So to be a part of that decision-making, they also need a bit of context and a bit of information. So there's some sort of background discussion and coordination that has to go on before we can collect the samples. And then after we've done the sampling, I have this Excel file that I send out to the growers because I need to collect some information regarding field management. So I just took some screenshots here, but essentially what I'm asking for from them is for each field that we've sampled from, I want to know what nutrient inputs went on to that field. I want to know sort of the recent information around cover cropping that might be going on for that field. I want to know about yield information for that field. So here I have this as sort of like a weight per acre option, but some growers don't like to work with that. Instead, they'll report back, give me sort of a rating. So like below average or good. And that is good enough for what I need from yield for the most part. So there's sort of this background information that I need from growers as well. Okay, so once I have collected information from the growers, I'm going to take that and provide some results and interpretation back to them. And there's sort of 3 different packages usually that we do with growers. So one is just straight up the lab test information, no interpretation other than maybe what the lab kind of provides on their reports as a standard. Then we have these nutrient report cards that we've been doing. So this is mostly focused on soil samples taken in the fall. So I should mention that the soil sampling we do for the most part is in the fall, but we do some spring sampling as well. So these fall samples allow us to kind of look back on the past season. These are the certain inputs we used. How did we kind of shake out by the end of the season? And then we have this input recommendations package. So looking forward into the next season. And I actually need a little bit more information that I haven't mentioned yet for this particular option. So I need cropping plans from the growers, what they're expecting to grow, and also what their target yields are for those different crops. Okay, so I want to dig a little bit more into the report cards and the input recommendations and just give a bit more clarity about what actually is involved there and connect it back to some of the information that I've requested from the growers. So starting with the report card, so I've just taken some screenshots again of an example for one specific field. So I take the information that the growers provided to me, and in this first table here, this is basically just a summary of the input information that they gave me for that field. The next table is a summary of kind of like what happened in the season. So first we've got some yield information, and then we have reporting back of some of the soil test values summarized here. And one thing I want to point out is for N, P, and K, I haven't taken like a copy paste from the soil tests and just put those values directly here. There's already been some level of interpretation. So I've taken the values from the soil tests and I've converted them into different values that have certain rating systems developed in BC. So for P and K, they've been converted to Kelowna values. For nitrate, I've put it into kilograms per hectare as a unit. So this kind of relates back to ratings, which can then be used for interpretation. And some of this also relates back to ratings used in the AEM code. So for those of you that don't know, the AEM code, that stands for the Code of Practice for Agricultural and Environmental Management. And this is sort of the regulation that we draw on the most in our reporting and is of interest and value to the growers. So we're
Hi.
Hi.
Oh, nice.
Oh, can you hear me still? I'm going to take
Yes,
that
we
as
can
a
hear you on online just fine.
Okay.
And someone
Okay.
else.
Okay, great. Thanks, Shabtai. Okay, so the next part of my report here, the last bit, is I have a table of actual interpretation. So adding some commentary to that interpretation. So I have basically taken this information about what was put onto the fields, what the yields, what sort of yield happened there, what happened with some of the nutrients. And then I have these comments basically bringing that all together to make some indications of how efficiently some of those nutrients were used, how good was nutrient management for some of those things. And I also have this note here at the bottom. It says next soil sample, and that's directly connected to the AEM code. So there's requirements around soil sampling intervals, so we're commenting on that as well. Okay, so moving away from the report cards into the input recommendations option. So with the input recommendations, I essentially take all that information that I was using for the report cards, and I put it into this nutrient management calculator that has been developed over the past several years by the BC Ministry of Ag and Food. So in this calculator, I put all that information in, and I'm able to sort of play around with different input options. And the way that I can do that, so the way that the calculator operates for that is based around the agronomic balance for NP and K and the crop removal balance for MP and K. And so using these two balances together, I can make sure that I'm meeting my crop nutrient requirements while also not grossly exceeding my crop nutrient requirements. So then, without getting into the nitty-gritty of how the calculator works, et cetera, this is just a tool that allows me to play around with input recommendations. And at the top here, there is a reporting option. So for some growers, I just share direct reports from this calculator. But I have also created my own summary, which takes information from that calculator. So I've got crop removal balance information here, agronomic balance information here. I've summarized it together into a table. And then underneath this sort of summary table from the calculator, I can put my recommendations and some further notes on those recommendations. And so this is where I can also take into account, like, what are the inputs the grower is interested in using? What, how have inputs worked out for them in the past? So I can kind of take the calculations from the calculator with a bit of a grain of salt, incorporate these other pieces of information to create my input recommendations. And in this case, the grower wanted a scenario where they were able to use compost and then a scenario where they were using no compost. So it gives me some options to meet what the grower's needs are. So one thing I want to say just generally about all of these reporting back to the growers is how important it is for me to meet with those growers and actually go through the results. So I'll have at least one-on-one meeting with the grower, and it's an opportunity for them to ask me questions about these written reports, as well as for me to ask them some clarifying questions if certain things aren't making sense. And often there'll be some revisions that come out of those meetings, or maybe they'll have requests for additional information that they really are interested in. So this component of having a follow-up meeting is so important to actually make those written reports be of value to the growers and lead to implementation. So talking about meeting grower needs, for one, through this process, we're providing them with important records. Through the AEM code, again, there are certain record keeping requirements that have come into play for growers. So around soil test values, field management records, and through this process, we're helping them to have those records put together. And in particular, we're answering two important questions for the growers. So one is, was what I did last year good or bad? And this is from an environmental perspective, agronomically, according to regulation. And the other question, and this is maybe the most important one for a lot of growers, is what should I apply next year? And this question is answered even through the report cards, mostly as indicating potential adjustments. And then, of course, through the input recommendations route, there's really specific input values, very targeted. Through this process, we provide what I think is really valuable one-on-one time for growers to spend time with an expert in the field of nutrient management to ask questions, work on solving some of their problems. And to me, this is knowledge transfer. And lastly here, also through this process, because it's a paid service, as opposed to like an ongoing research project, the growers can say to me, hey, I need my results by February 1st, because that's when I need to make my fertilizer orders. So that's really different from when I was doing my master's, for example, and I was reporting back to growers. By the time I actually had that meeting with them, it was like a year out of date based. They had moved on with their management. So that's another component that we're meeting here. Okay, and then finally, just some challenges or maybe just realities to consider when doing this type of nutrient management work with growers. One is that getting that field management information in that Excel file from the growers can be challenging. They're busy. Also, that Excel can be daunting to some people. There's quite a bit of information I'm asking for that maybe they haven't had to provide in that sort of format. So for some growers, I will show up to their barn and we will go through it together. We'll talk it through on the phone so that they don't have to do that Excel file on their own. One aspect of this also, so this is more connected to the soil sampling process. So having good knowledge of the fields. In my case, for the work that we're doing, we're often, for the most part, working with clients that we've been working with for years. And so we have field maps. We're quite familiar with their different field locations. And even having all of that information established, there's still sort of mix-ups and miscommunications that can happen with soil sampling. So there is a need to spend time and energy in making sure that that information is gathered, and I think would take more time if I was in a different scenario. Okay, this next point of trust, just to be frank, there are some growers who don't really trust the government. And so there are scenarios where growers have received maybe some free interpretation of some form through a free government related program. And they've said to me that they don't trust it and asked me to review it, that kind of thing. And I think it's because there's like a questioning of the motives behind those recommendations. Is it just solely environmentally based? And so they're going to end up under applying nutrients, that kind of thing. So it's just a very real barrier that needs to be taken into consideration. And then also, I don't think this is necessarily a negative thing, but practices are slow to change. And to be fair, like if I'm working with a grower, I don't want them to make one big drastic change. And I'd rather they try something small and see how that goes and then continue to incrementally make some changes. So that's just a reality to consider as well. And for all of these points here, there's just a couple of skill sets that I think are important to apply. So there's skills in persistence and then also skills in relationship building. And I know that we're here as a part of, this is a data management workshop. And so conversations are maybe a bit more analytically focused, but I just also want to highlight the value of these particular skills in the eventual success of implementing those protocols for sampling. Okay, and that's it. That was my whirlwind through that. And I'm going to stick around also through some of the plenary discussion to be able to answer questions and kind of contribute to discussion as well. So thanks so much, everyone. I'm going to pass things over to Shauna and Shabtai.
Okay, so Jude's going to stay on for this section. So I'm going to pass things now to Shabtai Bittman from Agriculture and Agriculture Canada to present. The reason why we started with Drew is because I know for these projects, a lot of people want to be doing nutrient management planning with the farmers that they're working with. And that's part of the value of the project for the farmers is getting this extra information. So I think it's a nice context of these are the types of sort of contracted services that farmers are already using. And I think ES Crop Consult is going to be working actually for some, like for field veg, maybe others doing this. And now Shabtai is going to talk really about some very similar types of information that can then be used to get the nitrous oxide estimates, which is one of the goals of the Living Lab. So Shabtai, we can see your screen, we can see you. And so I think if you unmute yourself, you can go right ahead.
Oh, thanks very much. Can you hear me?
I can hear you online.
Yes. Okay. Well, no one is saying they can. So Very happy to be here from, as I said before, downtown Toronto, far away from home, which is where you are, very close to my home. So very happy, and I really enjoyed the 3 previous talks. It's a tough act to follow. So I'll do my best, and I'm going to talk to you about, as Sean was saying, nitrous oxide estimates and farm nitrogen budgets and how they come together. And I worked on this and all the work that we've done with Derek Hunt extensively, and there'll be some of his particular information at the very end. So why is nitrogen important? Well, we know that nitrogen is the most abundant of the essential nutrients. All the essential nutrients are essential, but in plants, 1 to 5% of the dry matter is nitrogen. And in protein, 16% is nitrogen. It's obviously important to get a lot of nitrogen into crops. And uptake from soil is necessary for plant growth. And plant protein is needed for humans and livestock. So nitrogen is important. But there are concerns about nitrogen inputs in agriculture, and plenty of them. The inputs of N and other nutrients, as you heard from Drew, they must be carefully balanced with the outputs. If inputs are too high, there will be environmental losses. But if they're too low, you may get into a situation of soil mining. So the next point is that each nitrogen atom that's released into the environment can be incorporated into a succession of nitrogen molecules from one to the other to another, each of them having potential environmental consequences. So it's not just one outcome from one molecule or one atom that's being released. It could be multiple outcomes. You see that in a sec. So N lost to the environment enters into a cascade of transformations and transports. So this has been shown in or described in something called a nitrogen cascade. And this is intended to depict what happens to nitrogen when it's used in agriculture and what's the outcome. So you put nitrogen in, all the nitrogen you put in has to be accounted for in some way. It all goes somewhere, and none of it just simply disappears. So you see in the green box here, this is your agricultural system, and the inputs are fertilizer, mainly some atmospheric deposition from lightning, and nitrogen fixation, and they go in. And then once they're circulating in the farm, they're producing products, which is down here in the green, and that is the food that we get. But in addition to that, we get losses to the atmosphere, and we get losses to water. And so those are the atmospheres, these yellow arrows, and they're everything from N2 gas to nitrous oxide that we'll be talking about more, and even nitric oxide. And a big one is ammonia, which is the one here. And ammonia goes up into the air, and then it gets redeposited. It can be redeposited nearby, or it can be transformed into fine particulates by reacting in the atmosphere, and then it can move long distances. And then it goes into the ecosystem, and then what happens to it? So I'll just say that we in Canada and maybe North America haven't paid a huge amount of interest to ammonia, but in Europe there are regulations that each country must abide by, and not to exceed their ammonia emission ceilings. It's huge. It's more rigorously enforced than greenhouse gases. If they do exceed, they will be forced to pay penalties. And farmers themselves, in the Western European countries anyway, they're regulated. So for example, in Denmark, if they want to produce more pigs on their farm, they have to cut back on emissions per pig in order so that their overall emissions are not exceeded. And in Germany, there's a huge problem right now with a switchover from calcium ammonium nitrate to urea, which has a higher ammonia emission factor. So it's big. But then what happens is, okay, so then we're talking about nitrous oxide, okay, and that's what, this is the primary emission of nitrous oxide from manure and from fertilizer and from other farm sources. But in addition to that, the nitrogen that's leaving the farm and going into the atmosphere or going into water also produces nitrous oxide, and that is called secondary emissions. So all of these have to be accounted for in terms of nitrous oxide emissions that agriculture is responsible for. And just to show you what the Canadian nitrogen budget looks like, this is a recent paper by Karimi et al., mainly out of Lethbridge. But what it shows is the total input of nitrogen into Canadian agriculture. This is in teragrams, which is 1 million tons and of nitrogen. So you can see there's a balance is 3.8 goes in, 2.3, let's say, goes out, and 1.5 is left over as surplus. The efficiency is just under 60%. And the inputs are from fertilizer, from biological fixation and lighting, as I mentioned. The outputs are crops and livestock. And the losses are gaseous losses and leaching losses and runoff. So why is nitrous oxide a concern? Nitrous oxide is emitted from microbial processes when ammonia is oxidized into nitrate, and that's called nitrification. And when nitrate is reduced to N2 gas, dinitrogen, which goes back in the atmosphere, and that's called denitrification. The latter is usually the greater pathway and occurs in wet but not saturated soils. Saturated soils, all of the nitrate gets converted to N2, and there's no nitrous oxide. But if it's not fully saturated, then that's when you get the high emissions. In Canada, agricultural soils account for 75% of the national nitrous oxide emissions. And of importance, there's been a 50% increase since 1990, and it's mainly attributed to higher inputs of fertilizer. So on the other hand, we have Canada's strengthened climate plan, which is a commitment to reduce or to set national GHG reductions at 30% below 2020 levels. So obviously we have a strong need to be concerned about nitrous oxide. So how is nitrous oxide, and how are the emissions estimated? So Canada and most other countries report their emissions to the Intergovernmental Panel on Climate Change, which is more frequently known as IPCC. And the methodology is fairly standard in its general context, and that is that you have emission factors for different products and different activities, and they are multiplied. The emission factors are multiplied by the activity itself. So how much fertilizer is being used, how much manure is being spread. So the calculations can be made at 3 tiers. There's a basic method, which is the default, which is tell you in a minute. And then there's the intermediate level, which is the national specific, where countries have come up with their particular national emission factors that they've developed from research that they've done. And then there's process modeling, which is the gold standard, but it's still not widely implemented because of the fact that the models themselves are still in development, and the amount of data that's required to run those models is huge. But it's in development, and I think Canada uses the models to help develop the emission factors that are then applied in the standard way. So currently, the current default emission factor for nitrous oxide is basically 1%. It's 1 kilogram or 0.01 kilograms of nitrous oxide nitrogen per kilogram of nitrogen applied. And that's the default. And if you don't know anything else, then you will have to do that, multiply all the fertilizer you're using, all the manure you're applying, and so on, all the nitrogen fixation. And you would multiply by that amount and then tally it up. And so you have the list: fertilizer, organic amendments, crop residues, soil mineralization. Soil mineralization is interesting because normally it's not really included in the calculation, except where practices are such that they lead to a net release of carbon. So land use change and climate change and summer fallow are 2 of these processes that do have to be accounted for in terms of nitrous oxide. So a couple of points. One I've made in a sense that there is secondary emissions. So nitrogen that leaves the farm, let's say ammonia emissions from a manure storage, that will be deposited somewhere, and that will lead to nitrous oxide. That's the assumption. And so there is an emission factor which is equivalent to that which is the direct emissions. It's 1%. Okay. The second point is that with this method of calculation, you're actually not capturing changes in farming practices other than the inputs. So it's only really the inputs that are going to affect the calculation of emissions using the way the emission inventories are being done until such time as we get better and more specific, more critical emission factors developed. And there's work going on, but it takes a long time. So here are some examples of Canadian emission factors, just to give you a sense of it. And these are under development. There's a reference there if you want to read more about what is being done and what the approaches are. But you can see that organic nitrogen, which is, let's say, manure, is slightly lower than synthetic. Crop residues have an emission factor. Then you can see that the emissions are quite a bit higher on fine texture soil and coarse texture soils. And then I have some BC figures, which is there's just a universal BC N2O emission factor for dry areas, the interior, and for wet areas and irrigated land, it's 5 times higher, but still only at 1. And then there's the secondary emissions, which are for BC are 0.5 on dry areas and 1.4 in wet areas, and 0.75 for leach nitrogen, and that's as of a percent. Okay. And this is just to show you that there are different emission factors in different parts of the province, different parts of the country, different provinces. Won't dwell on it, but there's some changes. The difference between the light blue and the dark blue is just some impending changes that are being talked about, but haven't been implemented yet. So we do have some measurements that we've taken over the years, and I'll show you just a few of them. One of our tasks, I think, this coming year will be to gather up all the data that we have and others that produce, like Sean and others have produced in BC, and try to put it all together into some kind of coherent story. But here we see that this is a 5-year study, and so 5 full years of applying manure or fertilizer or treated manure onto grass. And the emission factor that we get, instead of, let's say, the default UN 1%, we get 0.084% for fertilizer and somewhat less for manure. And that's consistent sort of in general terms with what is reported by others. Another point I want to make here is that there's about 10,000 measurements that went into making this table. Okay, so I mention that because this is the problem that we have with the living labs, is that in order to take actual measurements on farms, you have to go there something like 50 times in a year. And each time you take one measurement in one plot, it's actually 4 measurements because you have to see the change over time. So I won't get into the detail, but it's very, very labor intensive. We won't be doing more than a few farms in southern BC. And just to further emphasize that point, here, this shows summer and winter emissions, and about maybe a fifth or a quarter of all the emissions happen in the wintertime. So at least for us on the South Coast and Lower Fraser Valley area, we need to measure throughout the year, which is one of the reasons we have to take so many measurements. So some places don't do that for various reasons, and then they just use a fudge factor for the wintertime emissions. There are problems with that because our 25% is actually lower than what they would have on the prairies at maybe 30 to 40% wintertime emission. And that's due to the freeze-thaw cycle. So it's important. So just some more numbers. This is corn. This is when you put manure on bare corn land versus at the same time putting the same amount of manure on grass. And there's much less emissions when you put it on grass because the grass takes up the nitrogen. There's very little free nitrogen for the microbes to denitrify. And as it would be on bare land without the crop until the crop is planted and grows. So you can see that. And so this will be the last one. And what this shows is farming systems. And so the top line, corn and grass, the red, and that shows what the farmers are actually doing. We replicated that on the farm, rates, method, and so on, crops. And then we find that the emission factor for corn was 0.58, so over 2 years. Carson was heavily involved in this work. Thank you, Carson. And we've carried this on now, and we're trying to get the next 3 years of data put together. So we have 0.58 and 0.42 for grass. Now, what I want to show you is now we've implemented BMPs, but not BMPs for nitrous oxide. in this case, in the injected sludge, is BMP for phosphorus utilization. So we inject sludge. I won't get into the detail, but doing that to get better use of phosphorus, we almost double the amount of nitrous oxide. And then we added a cover crop, which should reduce the nitrous oxide. And it would have if we didn't also add fertilizer or manure in this case, because the farmers, the dairy farmers, want more crop. They don't want just the cover crop to sit there. They want to harvest it and get product out of it. So when you do that, that's increased the overall emissions for that piece of land. However, so now we've almost tripled, maybe 2.5 times the amount of emissions by trying to do other good things. But now we put in some nitrification inhibitor, and these have been around. Some of these have been around for a long time. There's new ones around, and we can bring it back all the way back to what it was pretty well. So we can get all the benefits, and then we can also suppress the nitrous oxide if we have a good strategy. And more or less the same story with the grass. You know, we 2 different BMPs, and then we push it back to what it was at the beginning, and still have the benefit of those BMPs for the grass. So so that gives you like an idea about looking at the system as a whole and the complexity of doing that, because trade-offs are a big factor. And the way to try to reconcile some of this information, and you heard about it very nicely from Drew, is to do nitrogen budgets. So we're going to talk about nitrogen budgets now, and why they're important, and how they fit with nitrous oxide emissions. So so what is a nitrogen budget? It's very simple: inputs minus exports, and that's the surplus. Okay. So basically, we have 2 kinds that we can think about on farms. There's the field budget, which I think is what mainly Drew was talking about. So it's how much fertilizer, how much compost, how much manure has gone on, how much crop is taken off. And that is a field budget. But there's also a farmgate budget, which is a bit different. And the farmgate budget is how much fertilizer have you brought to the farm, but also how much feed have you brought to the farm, how many animals have you brought to the farm, and then how much has been exported in terms of crop and animals. There's 2 kind of fundamental differences between these, besides the obvious ones I mentioned. One is that the manure is treated differently in the 2. In the farmgate budget, unless you buy or sell manure, which most farmers don't, then manure doesn't come into it. It's an internal cycle. It is important, however, for the field budget. The other one is that losses that take place from buildings and from storages in other parts of the system, they do count in the farmgate budget, but they don't count in the field budget, because when you apply the manure, that's already net of what's being lost. So Drew does not have to calculate how much has been lost. He just knows how much is being put on. But with the farmgate budget, yes, that becomes a part of it. So now I'll show you kind of diagrammatically what this looks like. And this is taking advantage of this idea of hole in the pipe or leaky pipe model. So here we have field inputs, which we've talked about, and they're listed. I'll show you the list again, and Drew has spoken about it. It's a field budget. And then the outputs. If your inputs exceed the outputs, you're going to have leaks, because the nitrogen has to go somewhere. And these are the main leaks. There's ammonia, there's N2 gas, there's nitrous oxide, and there's leaching and runoff. And so in order to mitigate the losses, including nitrous oxide, you have to minimize the surplus, because the surplus has to go somewhere. But the same token, if you can reduce the escape routes, if you can reduce the losses, then it gives you the opportunity to become more efficient all the way through. So you really need to tackle it both ways. A key element in all this is these, I don't know how well you can see it, but there's little asterisks: fertilizer, manure, effluent, nitrogen fixation. Those are the items that are used for emission factors. So if you have this information, then you can estimate ammonia, you can estimate nitrous oxide emissions according to the IPCC methodology. And if you apply the country-based emission factors or the regional-based emission factors, and you'll do even better. And that will give you your nitrous oxide. So how would you improve the farm? Is by reducing these inputs. How do you reduce these inputs? Well, you can just reduce them, or you can make the farm more efficient and find ways to do it without losing production at the end of it. Okay, so that's the key. how do you reduce emissions by reducing inputs and then and not having negative consequences as a result. So direct effect, a direct connection between nitrogen budget information and calculations of nitrous oxide. Now, we want the BMPs to show that ideally, I mean, this is what would be nice, that there's less nitrogen being brought into the field, and therefore that can stand as proof of lower nitrous oxide emissions based on IPCC methodology, which is accepted worldwide. So again, we've kind of gone through it. It shows you here again where the stars are. These are the values that if you have that, then you calculate the N2O emissions and you've got it. Okay, and now we want the BMPs to have lower fixation or to substitute a lower emission. So for example, if we use manure more efficiently, we should need less fertilizer, and therefore that fertilizer nitrous oxide emission factor will go down. Okay, that's how the system can work altogether. And now this is the farmgate budget, and it's essentially the same idea. Okay, and I already mentioned that here the losses from buildings count, because some of these losses will actually be ammonia loss from manure storages, because what you bring into the farm and what you take out of the farm, all the losses that happen on the farm, whether it's in the field or in the buildings, they come out and they're part of that surplus or that imbalance. Okay, and but the manure itself, we don't really need to know how much has gone on. That's an internal it's an internal phenomenon, but it doesn't affect the calculation. And again, okay, so this is a list. So what we can do with these numbers is we can calculate the surplus, and we can compare different farms, different BMPs, and we can calculate nitrogen use efficiency, which in itself is a very important parameter to look at. So I brought this in, it's kind of like, so I mentioned nitrogen fixation. I didn't say too much about it. In the publication by the Environmental Defense Fund, they give a way of estimating nitrogen fixation. All the other things we can kind of get at. Nitrogen fixation, we have to find clever ways of estimating. So there are ways of doing that. I won't dwell on it, but I wanted to make sure that it's understood that that's one of the inputs that needs to be taken into account. And as Drew very nicely said, there's a bunch of other information that are needed in order to render interpretation of what has gone on. I won't go through the list. Drew's already mentioned a lot of it. But the point is, there's a lot of farm practices information that are needed in order to make this information more meaningful. So now we have the overall assessment of what does this all mean in terms of efficiency. So as you have increased surpluses, you get increased losses, and the increased surpluses will give you increased losses exponentially. And this is considered to be a safe zone. If you go under 25 pounds per acre, essentially equivalent to 25 kilograms per hectare, this is a US publication. So if you go there, then you're in danger of actually removing nitrogen from the soil, like mining it, in effect. If you go over, then you're in a surplus situation. So they estimate for their system, which is a corn soybean system, it's 25 pounds is kind of the low end, and 75 pounds, they don't want to go, or 80 kilograms per hectare. They don't want to go above that. And that's the safe area that they want to work on. Now, if you've got that measurement of the surplus, this is the real interesting thing here, that this is new and they've come up with it. And this is a very bona fide organization. And the scientists that have done this are top tier. They're the best. So this is, I think, well established now. I mean, it needs to be proven for our region and so on, but it's based on very good science. And what they've decided to come up with is that they can convert the surplus value, what they call the imbalance value here, and apply to a very simple equation, and from that get nitrous oxide emissions. And you can see here in the text, you'll see when you have access to this, that if you have 25 kilogram surplus, that's about 1.6 kilograms per hectare of nitrous oxide. And if you have 125, you're up to 2.5 kilograms of nitrous oxide nitrogen. And they also a bonus is that they can also calculate the amount of leaching that takes place in their system. We need to test this. And why do we need leaching? Well, of course, it's important in its own right, but there is a leaching emission factors for nitrous oxide. To put it together, this is kind of what it looks like in graphically. This is the top triangle here is where nitrogen use efficiency is above 90%, probably the soil is being mined. I'll show you an example. And down here below 50%, that's considered inefficient. And you want to stay above this, minimize the surplus line. So you don't want to go where you have greater surplus and you don't want to have lower yields. So you have to take all that into account. And I won't dwell, go into too much detail there, but here's what different farming systems look like. So this is grain with this high input and high output. Now we have certain crops like grapes, which have low input and low output. And then there's other crops like tomatoes and peppers, typically, that have high input and low output, and they're just less efficient. And there isn't necessarily something you can do exactly about that, but within each, you need to find the best way to handle those crops. Also interesting is crop rotations. So I mention this because we want to make the case for doing the nitrogen budgets for more than 1 year, basically every year. And that's because, especially if you have rotations, it's also for climatic reasons and other things. But if you have rotations, then the different cropping systems in your rotation, they'll have different nitrogen use efficiencies. And then when you put it together, you get this graph here that shows this system, this, and where they fall in the nitrogen use efficiency. But the point is that different parts of the system have different efficiencies, and it's the whole system that counts in the end. And this is a Canadian estimates of nitrogen use efficiency. It's only crops and what's happened over time. So the point I really wanted to stress here is 1960s, you're above 100%. The reason is there was a lot of summer fallow in those days, and a lot of that nitrogen came from summer fallowing, and that was mining the soil, and that's what we have to put back in now, not just the nitrogen, but the carbon that goes with it. And it has generally gone down, and part of that is because of the reduced summer fallow and the reduced tillage, because tillage with summer fallow is what really increases the nitrogen release. So just to show you very quickly here what livestock systems look like, and this is a recent paper from Europe, and it just shows that when you look at these nitrogen budget things, they look different in different regions, different countries, different types of industry sectors that are present. And this is the kind of data that we could produce, not exactly like this, but something along this line where we can see where the inputs are, there's feed input, there's fertilizer, manure input, there's crop output, there's losses, there's inputs, and so on. So you can compare different farms, different regions, different sectors, and so on. So it's a way of using this kind of information. Now I'm going to get to the very last part of the talk, which is, so how do we do better in terms of not just reducing inputs, but how do we understand better the nitrogen system? How can we just simply reduce nitrous oxide by better practices as opposed to just less nutrients? So one of the things we found, and it's depicted in these two graphs, is that you have conditions under which you have very high emissions, and you have other conditions which emissions are much, much lower. And so where soil temperature is high, together with soil moisture being high, which is over here, then you have real spikes, really high emission levels, and they really contribute to the annual total. And where you don't have either one or the other, then they tend to be much lower. And the same with high nitrate levels in the soil. So high fertilizer and high moisture will give you these spikes, these peaks. So we need to understand the dynamics of the nitrogen in the system. To do that, Derek, who will be giving you a workshop soon, has developed this bespoke nitrogen modeling for farmers using a model that he developed called NLOS, which is NLEAP on Stella, and NLEAP was developed by USDA. But Derek has put it onto this icon-based system, and this is what the model looks like, and a small part of it, but this depicts all of the lexicon of the model. So if you know these 4 terms, or 5, then you can model. You can just pull down menu and you can actually model. And the model is a dynamic model, and it's a process-based model So it's not just a calculation, and it does daily time steps. This is what a portion of it looks like in the actual model. This is the actual thing. And this shows you denitrification and crop uptake from the topsoil layers. And all this can be drawn by anybody. You just have to parameterize it, which is not easy, but this has been done. But we can tweak the parameterization without needing to go to modelers to do that. We can do that ourselves. So the unique aspects of this NLOS model is that you can do coupling in real time. You're able to enter data for a particular field, particular management practice, a particular year, and using the weather data of that year. And you can work through an innovation cycle so that each year you learn from what has worked and what hasn't worked in the model with the measurements you've taken, and then improve the parameters because it's easy to do. And the benefit is that the real-time internet format allows most of the recent extension research information to be implemented into the model. Last slide, I think, other than the conclusions, last slide. And this shows, and this relates to what Drew was was saying. So I thought that was really nice. So when you take soil samples, you get a lot of very useful information. Obviously, we all do that. We all like that. But we don't always know the context. So here's an example. This is actually work done by the Soil Conservation District in Whatcom County. And they did this over another number of years, Chris Clark. And this was a method of tech transfer that they were using and telling farmers how to interpret their PSNT, which is your, say, lead, June, nitrogen test in corn. This is in corn. And this is your PSNT, or this is, sorry, your post-harvest test. And so you can see if you take this sample here, which was in this case, or if you waited 1 week and the sample would be down here, the reason it would be lower is because it's leached. Okay, that's what happened here, is that there was leaching that's taken place. You wouldn't know that from your samples, but you would know that from your model once you develop confidence. And at least to a general extent, Chris, who was a very, very good extension agent for them, worked for years, did have confidence that it worked pretty well. And you can see a different scenario down below where it was a different set of conditions, and the soil samples captured the location, but to interpret the data, you need the model to know where it is. So that's what we hope to do on farms, interested farms, just a handful at the beginning, to work with them to test out and put into practice this model as Chris did, and we can do that with multiple crops. This is right now just for corn, but we had a grad student in Quebec that used it to do protected agriculture for, I think it was tomatoes and cucumbers in Quebec, using blood meal instead of fertilizer, and it worked. And I used it for his PhD thesis. So in conclusion, I've probably gone over time. Sorry. Canada is committed to reducing greenhouse gas. Reducing N2O emissions from agriculture is an important part of this. Estimating emissions is done by emission inventories and based on emission factors and activity data. And Canada uses empirical national emission factors to better estimate N2O emissions than the IPCC default. And reducing N inputs is simple, defensible system for mitigating emissions. Good management practices can minimize and prevent yield losses. And this can be documented with field and farm nitrogen budgets, and nutrient balances and surpluses are correlated with nitrous oxide emissions, so that reducing surpluses has a direct impact on estimates of nitrous oxide and leaching. And finally, the overall conclusion is that the field and farm nitrogen budgets can be used to help estimate nitrous oxide and to help manage farm nutrients for the overall benefit of the environment. And thank you.
Oh, perfect. Okay, sorry, just that little pause there to figure out muting, unmuting, to make sure we don't have feedback. Thank you so much, both Drew and Shabtai, for your presentation. I just want to make a couple of notes. So one, as Shabtai mentioned, the NLOS model that Derek has been working on, we are going to have a time, like a full 2-hour session, just Derek talking about that model and how it can be applied with different production systems, what information needs to go in, and how AFC can support that as part of the BC Living Labs work. And then also there was, Shabtai mentioned a few different things around emissions factors and emissions reporting federally. And tomorrow morning, Dan McDonald from Agriculture and Agri-Food Canada is going to be presenting about federal emissions reporting. So there'll be a chance then to go into more detail on those. So for our questions now, and we have about a half an hour for Q&A and still getting to lunch on time. Yeah, if you want to focus your questions around the nitrogen budgeting, a lot of the examples were in dairy, and so maybe in particular people want to ask questions around how this could apply under different production systems, or yeah, maybe just questions around like how you're sort of envisioning this happening for your commodity in the Living Lab projects. So anyone should be able to ask questions. You can ask questions in the room. If you're online and you want to ask a question, just raise your hand and Mustafa can unmute you so you can ask your question. Yeah, so who wants to kick things off with their first question? Don't be shy, guys. I know you did want to stop talking before.
They want lunch.
They want lunch. Well, they have to wait half an hour for lunch.
Oh my gosh.
Oh my gosh. Serena, thank you.
Sure, yeah, I'll throw maybe a random question, but I noticed, Shabtai, with all the emission factors that you were listing, it was all for liquid manure or slurry manures. Has any BC work been done on solid manures, and how does that change the equation?
Yeah, and that is a really good question. We have worked, you're right, we have worked around liquid manure mainly, but I just add the point that we also look at separated manure, and we've looked at the liquid and the solid fractions in different ways. I won't get into all the different things, that would take a while, but the solid fraction in some ways resembles solid manure. So what is solid manure? It's the same. It's just that it's kept it's stored in a different way. It's usually produced by beef cattle, but not necessarily. It could be pigs or it could be dairy cattle. But what is characteristic is that most of the ammonia, which is the readily available nitrogen, is gone. It's lost, and the C to N ratio is very high, which means there's a very little chance of leaching from this manure. But on the other hand, the nitrogen value is quite low, and furthermore, it's very difficult to implement better application methods. About the only thing you can do is rapid incorporation to try to preserve the ammonia that's still left in it. And you can't do that where you have no till. And even where you can do it, it takes an effort, and you have to do it fast. So logistically, it's difficult to do. Some of the emissions that take place would happen while the manure is being stored. But because the manure is stored dry, the emissions from the pile in terms of nitrogen oxide are quite low. So the overall emissions from beef manure, they use the same emission factor, but the total amount of nitrogen is less. So are you accounting for the nitrogen that's gone, that's evolved during storage? Well, not if you're just doing the farm gate or the field gate thing. So there's less nitrogen, but you have to put more fertilizer in, because you're probably not going to get enough nitrogen from that manure unless you're in a very low input system, or you have a lot of legumes. So if you have a lot of legumes, that fits, because then you've got the phosphorus and the potassium, which is still in that solid manure. So I guess it's a kind of a rambling answer. A follow-up question is accepted.
Yeah, maybe going back to the cattle and forage systems. I know this was a question for you guys around doing nutrient budgeting with producers, because it wasn't really an interest for them because they are a low input system. So I guess, one of the questions I have is, is it worth, will it be easy enough to get the information that it's worthwhile to do this? Shabtai, I know that you think it's definitely it's worthwhile for them to be collecting this information, and maybe you could just speak to that for the low input systems.
So
Um,
can you just repeat it exactly what, I kind of got the gist of it, but maybe just a
Yeah,
little bit louder for my
For the
failing
low-
ears.
Yeah, for low input systems,
Yes.
is it worthwhile for them to do this type of nutrient budgeting?
Oh,
As a-
yes, yes, absolutely. Yeah, no, absolutely. Okay, I got you well. Because, it all counts, right? And so if you have a low input system and maybe there's only 1/5 as much nitrous oxide, let's say, but there may be 10 times as much land. Like, so if you compare the amount of land for beef in BC, it's much more than the land for dairy. So yeah, I think it all matters. And at the end of the day, all the nitrogen you put into the system, whether it's fertilizer or in fixation, but all the anthropogenic nitrogen you put in, really, we need to be accountable for that. And you know what? It's also at the end of the food chain that we need to be. It's waste, it's human waste. It all needs to be accounted for. There's 2.5 million tons of nitrogen fertilizer and another million tons. I don't know if you caught that from my talk, another million tons of N fixation that goes into agriculture every year. What happens to it? It's nitrogen, like it gets denitrified, but eventually, but not before it does a lot of other things. And every year you have to put the same amount. So we need to find a way to mitigate that, to reduce the inputs. 2.5 million tons. The Fraser Valley, I figured we published a paper that showed, I think it was 20,000 tons of nitrogen that goes into the Fraser Valley every year as feed and fertilizer, mainly as feed, but also as fertilizer and food imports. And none of it leaves in a good way. It's just like a terminus. And other places are too. I mean, we just calculated for there, but you could calculate it for anywhere else. And so, there needs to be accountability. You bring in the nitrogen or phosphorus or whatever it is, batteries or, whatever it is that you bring in, you have to be accountable for that. And awareness is part of it. And when we talk about recycling, we often talk about the carbon component, not the nutrient component. So most of our recycling system, where there's anaerobic digestion, composting, or combustion, is all about using the carbon, and none of it is about using the nutrients. And that's a big mistake, because the nutrients are worth more, and they cause more harm. But it's hard to do. It's not because we're like, everybody's too lazy to do. It's hard. It's hard.
Are there other questions? Maybe tree fruit and wine grape folks that are joining, could be some questions there from your commodities perspective.
I also have a follow-up question for Shabtai, just based on some of you just said there, if I might butt in. I'm just, question about the field budget. So I'm just looking, thinking about the different inputs,
Right.
the different field inputs. And so okay, I can get information about fertilizer inputs from growers. I can get manure and other amendment information, crop residue information. But you just talked a bit about N fixation. I feel a bit hung up on how I would capture that information. Maybe that's a part of this protocol development as well. But could you speak a little bit more to that N fixation and how it would be measured to be incorporated as a part of the budget?
Yeah, it's there's been quite a lot of work done, not a huge amount, but quite a lot of work done on estimating that. And basically, there's a relationship between between the yield and the crop type, because some crops tend to have more N fixation than other crops. Fava beans are a huge fixer, by the way, and soybeans not so much, but they all do fix. And so it's the yield, what's removed, what's left. Okay, so if you produce, let's say 100 N of fixed nitrogen from your legume, and you remove 50 as grain, then you have 50 that goes back into the system. Okay, and so but do you know what that amount is? Well, that's where that information from the Environmental Defense Fund really tries to address that. But we also have information like Canadian studies that have been done in different parts of the country. We do need to do a better job with it, though. We do need to do a better job. Some of the nitrogen budgets in Europe, believe it or not, did not include nitrogen fixation. It's just mind-boggling. How can they not do that? But they, you know what? They don't have a lot there because they don't grow that many legumes. They mostly buy them from Brazil, like soybeans. So they grow grass and corn, and so it kind of, in a way, makes sense that way. But still, in some of their budgets, it wasn't even. But in Canada, it's huge. In the US, it's huge. Yeah,
Yeah,
I didn't
'cause when
show.
I imagine. Oh, sorry. Go ahead, Shabtai. Go ahead.
Yeah, no, I didn't show that the nitrogen. I mentioned nitrogen use efficiency in Canada was about 62%, I think. And then it's about 73% in the US. We use similar calculations. So why is it higher in the US when actually our practices are better in Canada? And there's two reasons. One is that they use a lot more soybean, and so that they buy less fertilizer, and so that helps. And the other one is that they use a lot more corn, and corn is very nitrogen use efficient because it's a C4 plant. It's pound for pound, kilogram for kilogram. It's more efficient than cereal crops, and it's evident because the percentage nitrogen in corn is about 1% in grain, or in the total product 1 point something. But wheat is at least 2%, 2.5%. So that nitrogen needs to be accounted for. So corn, so they have a more efficient system there, which is interesting. It's irritating too, because our farmers actually farm better. We do more fertilizer placement than they do.
Great. Yeah, thanks.
I don't know if I cut you off there. You may have wanted to ask something else.
Nope.
Sorry.
That's great. That's really helpful. When I imagine doing those budgets myself, as someone who's like familiar with budgeting in just a different context, that would be a hold up for me, would be how to account for contributions of nitrogen fixation. So yeah. Yeah,
and for particularly for cover crops, right? Because some farmers like to use, or alfalfa rotations. But there are ways we can sit down and work that out.
Cool. Okay.
Okay, thank you for that. And we have a couple questions in the room. So Jeff, I'll go to you first, and then Sean.
Gosh, Dr. I was just thinking, trying to tie back your nitrous oxide emission factors that you were showing for corn and grass with the different practices, where corn with cover crop was less efficient than just corn alone in the standard rotation. Did you look at the impact on soil carbon? Because we're currently talking about soil carbon and nitrous oxide in the same breath here. So if the NOx efficiency emission factor went up, did the soil carbon increase when you put cover crop into the rotation, or did you measure that?
Yeah, so we did that trial. We didn't do long enough but we now have it longer. Plus, we are hopeful that we're going to get a dairy cluster proposal to run it for another 5 years. And so we're waiting to hear. We made a short list, and the industry is very interested in that because they don't have so many long-term trials with dairy manure in the country. There's really only one other one, and that's in northern Quebec and the Normandin area, and they're part of our project. So we will be looking at exactly that to see, but all of it is a little bit of apples and oranges, but farming is apples and oranges. So if you compare things exactly the same way, you're not necessarily comparing them realistically. So, corn is not treated the same way as grass. If you apply the same fertilizer, same manure, the same rates to corn and grass, you can certainly find out which is more efficient and which isn't. But it's not what happens on the farm. The farm corn plant, they use 250 kilograms or 200 kilograms of nitrogen in one form or another, and they probably use 400 or 500 for grass. And that's the way it's handled, and that's how it more or less should be handled, give or take. So that's what. Even where it went up, you have to contextualize it, and you have to consider all the other elements. And phosphorus is one thing that we're very interested in because it's a big issue. If nitrogen is being hung up in the lower mainland, imagine phosphorus, which really has no place to go. It can't even go in the atmosphere. So we're trying to resolve a number of things together by an integrated approach. And when we use that, we call it the dual stream method. So we treat the liquid fraction and the solid fraction completely different. The solid, which is actually sludge, is precision injected into corn as a phosphorus source, and it works, and we published on that. And the liquid fraction is more efficient as a nitrogen source in the whole manure by quite a bit, while also loading less phosphorus. So this isn't a very specific answer, but it's just the point is that you need to, what we're doing with Living Lab is trying to come up with the right context. And we were also trying to do that in our experiments, but we can only go so far in the experiments, for all kinds of reasons, just the size and equipment and so on. We tried as much as we could, but we can do a lot more now going on farms and trying to do some of the same stuff.
Yeah, I guess part of that question is the whole notion of we're looking at this as a beneficial management practice. So thinking environment, economics, society, whatever. So you're saying, if we add cover crop into corn, we might increase the NOx emission factor, but there might be a whole bunch of other benefits to it that may actually be in total higher than the fact that we've increased that one factor.
Yes, and to tie that back, thanks for saying that. And for tying that back to the talk, which is the budget, so having that cover crop, and if it's harvested and fed and it actually makes excellent feed and bumps up your milk fat, as Nelson has found out recently, Nelson did in the UBC farm, so then you need to buy less feed, and you may get a little more milk, or and so then that overall equation, which is not reflected in those emission factors, but our study is intended to reflect that. I just haven't shown you all of it, and we haven't finished all of it, but we are looking at feed quality and what kind of feed supplementation you need and how to minimize that. And it gets quite involved, but even lax harvesting, so taking only 3 cuts of grass, and now we're trying to bring in some alfalfa into the system. And I mentioned that to you in our little discussion, because that's a very good target for the separated solids that we produce. They always say, okay, you can separate this manure. What do you do with the solids? What you do with the solids is you apply to alfalfa. Perfect. And then you don't lose that nitrogen fixation from the whole that you would with the whole
Thanks
manure.
for that. 'Cause, I think the point of the context is so important, and not just getting hung up on the numbers, the single measurements. Sean, I don't want to skip you, and then we'll go over here. So go ahead.
I just want to draw attention to the cover crops for a second and highlight that cover crops can be a sizable agronomic contribution in nitrogen. That I think we should really think about how we coordinate our estimation of that contribution. So there are a number of strategies to estimate. When you look at the information available, the book values for cover crops are not generated here. That data is all coming from elsewhere. We don't actually have a good sense of what the fixation rates are for cover crops. We're also trying to introduce new cover crops and cover crop mixtures. So going back to Drew's question, which I think she's talking about in vegetable systems, how do we estimate this? Then we need to be doing a better job of not just estimating, but measuring it. We need some better data on what cover crops are contributing to our system, and developing a data set that we can share with farmers so they're using localized values for what contributions are coming from those cover crops. And I think, we should talk about that, figure out the strategy on that.
Yeah, that's a really great point, especially when there's cover crops being used in different production systems in different regions. Could be a really good opportunity to do that kind of measurement. Do you want to ask your question?
Yeah, this was a question for Drew. So if I understand your process, you essentially send a spreadsheet to the producer. They fill out any information that they can about the crop, the acreage, amendments, etc. And then you can offer 3 different services: results, report card, input, recommendations for the upcoming year. I'm curious, do you do any analysis for your forecast and then compare it in the following year against kind of a retrospective? And is there a system that you can use to kind of compare that forecast data over time?
Ooh, that's a good question. So there are a couple of instances now where I have worked for subsequent years with growers who have opted for the input recommendation sort of option. So I do look at it, I'd say more on like a qualitative level of based on what we recommended and they might have ended up using that last season. How did that then feed forward into our post-harvest sampling that we did after that season? And then how is that reflecting back into input recommendations? But in terms of like quantifying that a bit more specifically, it would be great to do that. And I can't say that I necessarily have done that in my work. It's a really good question. Yeah.
Okay, thanks.